Hi students, welcome to my YouTube channel. In last video we discussed about the derivation of 1D bar element, that is stiffness matrix for 1D bar element. Today we are going to do some problems based on Excel bars. Here we have the first problem, that is the figure shows one dimensional bar subjected to an axial loading. Here we have one bar, it is fixed at one end, and another side we are using this force. Okay, so an axial loading, taking it as single bar element, so we have to consider this entire body as one body. Sometimes they will mention it as two body, that time we have to divide this entire body into two elements. Now it is single element, single body. Okay, so we have to determine nodal displacement, stress in each element, reaction at the support. Nodal displacement are q1 q2, stress is sigma 1 sigma 2, and reaction r1 r2. If you are considering it as a single object, so here we will be having node 1 and here we will be having node 2, and here we have the Young's modulus, that is 200 GPa, and area is 10 raised to 4 mm square, and here we have f1, that is 0 because it is fixed end, and here it is f2 10 kilo Newton, and the length of the bar is 1000 mm. So we'll do stepwise. So first we have to create the finite element model, in short FE model. Okay, the first step, finite element model or FE model. Okay, here we have one object, that is bar. We have to consider it as single element. Okay, this is node 1 and this is node 2. Here we have force F1, here we have force F2. Okay, here the displacement is Q1, and at node 2 the displacement is Q2, and here we have single element, that is E1, and the length is L. Okay, so after this we'll write the given data here. E is equal to 200 GPa, gigapascal, so I will convert that in megapascal, that is 2 into 10 raised to 5 megapascal. Okay, now area is 10 raised to 4 mm square, and L is 1000 mm, and F1 is 0, F2 is 10 into 10 raised to 3 Newton. Okay, so this is the question, and this is the first step, and this is the given data. So we will go for elemental matrix. Second step, elemental matrices, and we have the formula for elemental matrices from the derivation KE. Here E indicates number of elements, AE, EE, LE, this is L, 1 minus 1 minus 1 1. Okay, so for element 1, substitute E is equal to 1, and area, we know area is 10 raised to 4 mm square, and Young's modulus is 2 into 10 raised to 5 megapascal, and length is 1000. So K for element 1, that is 10 raised to 4 into 2 into 10 raised to 5 divided by 1000 into 1 minus 1 minus 1 1. Okay, so after solving this we will get 10 raised to 6 outside, 2 minus 2 minus 2 2, and here we have only one element, so element 1 is enough. Now I'll go for global stiffness matrix. Third step, global stiffness matrix, that is the summation of stiffness matrix for all the elements, but here we have only one element, so that is K is equal to K1, that is 10 raised to 6 2 minus 2 minus 2 2. Next, global nodal displacement vector. Global nodal displacement vector. So displacement vector we know that is indicated by capital Q. Here we have two nodes, so it is Q1, Q2. Okay. Similarly, global load vector. F is equal to again F1, F2. We know F1 is 0 because that is fixed end, and F2 is 10 into 10 raised to 3 Newton. In question it is mentioned as 10 kilonewton, so that it is 10 into 10 raised to 3 Newton. Okay. Now equilibrium condition, I will write equilibrium condition. We know already global stiffness matrix into global displacement matrix, that is vector, and into global load vector, that is F. So I will substitute one by one. 10 raised to 6 1 minus 1 minus 1 1, and here this is Q1 Q2, and load vector 0 10 into 10 raised to 3. Okay, this is equilibrium condition. Now we'll apply the boundary condition. As we have the body like this, here as force is 0, displacement will be 0. At x is equal to 0, the displacement will be 0, and at x is equal to 1000, the displacement will be question mark. That what we have to calculate. Okay, so as Q1 is 0, we have to eliminate this first row, first column as from the elimination method. Now I will write 10 raised to 6 into 1 into Q2, that is equal to 10 into 10 raised to 3. Okay, that is 2 into, here this is 2, right? 2 2 2 2 here as from this, so that 2 into 10 raised to 6, this into this, and into this Q2, that is equal to 10 into 10 raised to 3. Okay, after solving we'll get Q2 is equal to 0.005 mm. Okay, this is what we calculated the first question. In first question they asked nodal displacement. Nodal displacement at node 1 is 0, at node 2, that is Q2, is 0.005 mm. So now we have to calculate stress in each element. So first I will write it in matrix form. Q1 is 0 and Q2 is 0.005. Okay, that is Q. Next, stress. We have to calculate stress in each element, but here we have only one element, so that is sigma is equal to E by L E into minus 1 Qi plus 1. Here we have two nodes, Q1 and Q2. Just substitute the values. Sigma is equal to E is 2 into 10 raised to 5 divided by L is 1000 minus 1. This is 0 and this is 0.005. So sigma is equal to, see, first we have to multiply this into this plus this into this, then we have to multiply with 0. So anything will be 0, that is 0. And then this into this we have to do. After calculation you will get 1 megapascal, that is stress. Okay. Now the last one, reaction at support. For this we have formula, that is R is equal to K Q minus F. Okay, we know already K, that is stiffness matrix, global stiffness matrix, global displacement vector, and this is load vector. Just substitute the values. As we know, K 10 raised to 6, 2 minus 2 minus 2 2, and Q 0.005. Force at node 1 is 0, force at node 2 is 10 into 10 raised to 3. Okay, now we have to solve this so that we'll get reaction force. Here see, first here we have two matrices. Here the order is 2:2. For this order is 2:1. As these two are same, multiplication is possible. You'll get the answer in the form of 2:1. That is minus 10,000. Here minus plus 10,000. Minus, here we have 0. 10 into 10 raised to 3 means that is 10,000. Here this and this will cancel because both are same. Here we'll get minus 10,000. Here 0. Okay, reaction force at support 1 is minus 10,000 Newton. This will be Newton. Okay, unit is Newton, and at node 2 the reaction force is 0. So here we calculated first the displacement, Q1 is 0 and Q2 is 0.005 mm, and stress sigma, here we have only one element, so sigma 1 is enough, so that is 1 megapascal, and reaction at node 1 and at node 2. Thank you.